Okay, so welcome everybody to Relativistic Physics. Like I said, I have not been able to dedicate as much time to this class as I would have liked because I have to teach two other classes at the same time. And but so today is our first proper class, I suppose. Okay. Where is the? I've shared a course plan with you, right? If I'm not mistaken. So let me open that again. Let's just have a look at it. Now I'll share my screen. Okay, so the course plan is, we start with special relativity, space-time diagrams, and all that good stuff, tensors, relativistic invariants, coordinate transformations, and so on and so forth. Then we'll go to talk about the electromagnetic field. We'll talk about charged particles in an electromagnetic field, Klein-Gordon equation, and so on, then Dirac equation, Pauli equation. Did all of this time permitting. Now, one of the best books for relativity that I have encountered in my experience is this book by Andrew Steen, which is Relativity Made Relatively Simple. So you should obtain a soft copy of this book as soon as possible because it is a beautiful book. Then there is the standard text by Griffiths on electrodynamics. That is also a very nice book. Sometimes the explanations are a little bit too detailed for my taste, but you might actually like long and detailed explanations. So you should check that out also. Okay, but I won't be using any book as such. At points in time, it would be good to refer to Steam. If you don't have a soft copy, please let me know. I will provide you with one. Okay, so with that being said, let us try and use the remaining half an hour or 35 minutes that we have usefully. So today is lecture 1, January 5, 2021. And again, I hope all of you know how to use Zoom. If any of you don't learn, just go on the website for Zoom and you'll see lots of tutorials on YouTube and wherever. So you have an unmute option in Zoom, and please use that whenever you have a question. Not December, not. Okay. Now, so we are going to start talking about relativity. Okay. Now I will presume that you have had exposure to special relativity in your undergraduate. Is that right? Can you raise your hand in the Zoom window if you have not had any exposure to relativity? Not had any exposure to it. Okay. All right. So since I'm not seeing any raised hands or any other kinds of responses, I will assume that all of you have been exposed to relativity. So I won't go into great detail about the motivations and so on and so forth. I presume you all know about the Michelson-Morley. Okay, so one person raised their hand, but then they lowered it. Anji, have you not been exposed to special relativity as in undergraduate?
No, sir.
You have not seen relativity at all.
No, sir.
No. Okay. Okay. All right. Is there anybody else who has no prior exposure to special relativity? Okay. All right. So one person so far. So Anji, what I will recommend for you, okay, is you will have to do some reading on the side. Okay. So I will talk with you separately. But for now, I will, go with the majority, right? So, but I will have a discussion with you separately, okay, about how we can overcome that gap. Okay, so relativity, we have certain postulates. We have Einstein's two postulates, and we have the Lorentz transformations, which are the consequence of those postulates. Of course, the Lorentz transformations were invented or discovered many years before Einstein constructed his theory. That's why they call the Lorentz transformations and not the Einstein transformations. And the reason the Lorentz transformations were, the motivation for having those transformations was to explain the null result of the Michelson-Morley experiment. So the Michelson-Morley experiment was intended to detect the motion of the Earth through this medium called the ether, right? And the ether was postulated to be some medium which filled all of space, and with respect to which you could define it. So it provided a universal rest frame with respect to which you could measure the absolute velocity of any object, right? But more importantly, the ether was the medium whose oscillations corresponded to what we understand to be as electromagnetic fields, electromagnetic radiation, right? So you had Maxwell's equations. Maxwell's equations predicted the existence of electromagnetic waves, but electromagnetic waves, as the understanding was at the time and still is, waves need a medium to propagate in, right? So sound waves propagate in some solid, liquid, or gaseous medium, and same thing for water waves and any other kind of wave that you can think of. There is always some sort of medium, and the particles of that medium or the constituents of that medium, they undergo coherent motion. Coherent meaning that, synchronized motion. And that synchronized motion can be viewed as a wave motion when you look at this on a large scale. So then the question was, well, these electromagnetic fields, what is the medium of which these fields are the disturbances, right? And so this ether was postulated as the medium, and now, so if there is this medium, then well, you should be able to detect, you should be able to measure your velocity with respect to the medium. At least that was the thinking. And so Michelson-Morley experiment was conducted for that purpose. But the Michelson-Morley experiment gave a null result. So that meant that something was wrong, either with the idea of the ether or with our understanding of space and time. And so it took Einstein to realize that you couldn't just manipulate the equations of physics to explain the Michelson-Morley experiment. because that is what people like Lorentz and Fitzgerald and others tried to do. So they came up with this Lorentz-Fitzgerald contraction to say that the Michelson-Morley experiment, you get a null result because moving objects happen to contract in the direction of motion. And that contraction is just enough to counteract the change of the relative phase in this Michelson-Morley interferometer. So, so Einstein, took the bold step of recognizing that the Lorentz transformation isn't just something that happens to solid bodies. It's a property of space-time itself, and it describes the relationship between observers in different frames of reference. So, what is this Lorentz transformation, right? In the simplest case, it is a transformation between a spatial coordinate and a time-like coordinate, right? So we have x. So now, before talking about Lorentz transformations, let me introduce the concept of space-time. Okay, so since we are doing a graduate level course, all right, I won't talk about, I'll go talk about 4 vectors in space-time. So what is space-time? So, well, we know from relativity, with the benefit of hindsight, that space-time means that any point has 4 coordinates, 3 spatial coordinates and 1 time coordinate, right? And any such a single point in space-time is called an event, right? Now, what is the geometry of this space-time? So, like if you look at just x, y, z, right? Normal, just the space part. Well, this is a point which we say lives in R3, right? What is R? R is a set of real numbers. And, well, I'll leave the circles out. And since this is a pair of 3 real numbers, this point lives in R3, right? So now we add a 4th point. So one would suspect that these points, they live in R4, okay? And the expectation is almost correct, but not quite correct because of one important difference. The important difference arises from the fact that there is something called a metric. And the metric on this space is different from the metric on this space. Okay, so what is a metric? A metric is something that is used to measure distances, right? So for instance, if you have any 2 points in space in R3, so how do you talk about points? Now I will also introduce the index notation for this purpose. So when I have a vector v, right, I can write it like this: vx, vy, and vz. I can also concisely write this as v of I, where I is a index and this is a spatial index. So whenever you see I, j, k, etc. as indices, these will all be spatial indices. And spatial indices will take values from 1 to 3. Okay. So for example, if you have 2 vectors, u and v, you write the dot product of 2 vectors u and v. How do you do that? You can write it as ux, vx, and so on, right? Or instead of writing x, y, z, we'll just say u1, v1, u2, v2, u3, v3, and so on. Yeah, it's structured. You have a question? Okay, I thought you had raised your hand. Okay. So this expression is a sum over I over of ui vi, right? So this is the dot product between n and two vectors. Now, so if I have any 2 points in space, okay, let's say I have x1 vector, or I have vector, I'll write it like this, vector x1 and vector x2. Okay, that's probably not the best way to do it. Let me write it as x and y. Okay, and so this has 3 components, x1, x2, x3. This has 3 components, y1, y2, y3, right? So then now I can write the relative displacement between these 2 vectors, right? I can write delta r something like this is equal to y minus x, right? So if you think in terms of coordinates and so on, x, y, z, these are your coordinates, and you have 2 vectors. One is a vector r, one is a vector y, and the vector y minus x is this object, right? So this is all standard high school vector algebra, right? Everybody has seen this before. And now we have this Pythagorean theorem, right? So the Pythagorean theorem tells us that we can associate with each vector, we can associate a length, right? So if I have a vector x, I can associate a length with length squared, which is x1 squared, x2, sorry, yeah, x2 squared plus x3 squared. Or if it becomes difficult to, if the indices become confusing, you can write it as x1 bracket square, x2 bracket square, plus x3 bracket square. That way you know that this is the first component, the second component, and the third component. So one would also write this as summation of xi squared I is equal to 1 to 3. Okay. So one can write down the length of this vector x, and similarly one can write down the length of the vector y, right? And one can also write down the length of this vector r, right? And what is this? This is equal to I is equal to 1 to 3 yi minus xi squared, right? That's what this displacement r is, each of the component wise subtraction of these 2 vectors. So what I say is now is that these are 2 points in space. This is the point A, this is the point A, B, and I say that delta r is the vector, the displacement vector between these 2 points, and this delta r has a magnitude which is given by this difference, right? And another way to look to think about the same thing is that let's say that you have some point in space A whose location is given by some vector x, and you you change your position to some other point B by some displacement vector delta x, right? So then you have x plus delta x. So the location of the point B is x plus delta x. And then what do we say? We say that the distance between A and B, between these 2 points, is given by the magnitude of this delta x vector. So root of delta x 1 squared, delta x 2 squared, and so on, right? So this is what this is a metric. This is called a, and the way we would write this metric, another way to write this metric. Now I will introduce something which is called the metric tensor. So in this case, the metric tensor is something very simple. Okay. The metric tensor is simply the Kronecker delta, right? This is the metric tensor, delta ij. So if I want to write down the length of some vector, I have some vector x. I want to write down the length squared of this vector. How would I write it? I would write it like this: xi squared. Another way to write it is the following. I would take delta ij, xi xj, and sum over I and j. Ij is equal to 1, 2, 3. Right? So now I have a sum over two indices, I and j. But when I do this sum, I will get exactly the same result. All right? Is this clear? I hope there are no issues about this. Okay. Now I will introduce something called the summation convention, which becomes important for us as we go forward. And it's normally associated with Einstein's name, so we'll call it the Einstein summation notation, or I think convention is a better term. What is this summation convention? So in all of these expressions, what you have noticed for is that, so for example, this expression, right? What is xi squared? It's xi times xi, right? So you have this index I and it is repeating twice. Okay. Similarly, if you look at the dot product of two vectors, you have ui, vi. You have this index I and this index is repeating twice. Right? And if I write down this length squared using this delta, now I have two indices, delta I and j, and each index is repeating twice. So I have I and j that is being repeated over here, and I have so I is being repeated and j is being repeated, right? So whenever we have a repeated index, what are we doing? We are summing over those indices, right? So we are summing over this repeated index I over here and over these indices I and j. So the summation convention says that unless otherwise specified, whenever we see an index repeated twice, we sum over that index. Okay. So for instance, if I give you the expression ui vi, and that's it. Now your first thought will be, well, what is this expression? Because I don't know the value of I. But if we are using the Einstein summation convention, then what is this equivalent to? This is equivalent to the statement that you take this expression and you sum over I. So what is this quantity in the in the summation notation, this quantity is u dot v. Okay. Similarly, if I want to write down the length of a vector x, the length squared, how would I write it using the summation notation? I would write it as delta ij xi xj. That's it. No need to insert a summation sign because it is understood that since I is repeating, there is a sum over I, and since j is repeating, there is a sum over j. Okay. So this kind of a notation is very useful in linear algebra in general, right? So for example, say that you're talking about matrices. Let's say you have some matrix A, which has elements aij, and you want to talk about multiplication of matrices, right? So you have some matrix aij and some matrix B, whose elements again are some bij. Okay. And then you want to talk about the multiplication of these matrices. A, B is equal to some matrix C. Right? Now, how do we write down the elements of C? We say Cij, right, is equal to Aik, Bkj, sum over K, right? And K is runs over from 1 to whatever is the number of columns in A or the number of rows in B, right? So K, and if we assume that we are talking about our tensors in space or space time, then these are either 3 by 3 matrices or 4 by 4 matrices. So if these are spatial tensors, then K runs from 1 to 3, right? This is the standard expression for multiplication of two matrices, right? So if I use the summation convention, I will just write this as Aik Bkj. That's it. No need to put a summation sign. Similarly, let's say that I want to now there can be situations when this summation convention, you need to specify that you are not using it. As an example, if you are referring to the let's say the diagonal components of a matrix, right? So you would write Cii as a diagonal component, right? So this is the ith diagonal component. Right? But if you are using the summation notation, then what is this Cii? It is the trace of this matrix, right? Because according to the summation notation, it is the sum because this index I is repeated, right? You have to sum over it. Okay. So again, so in such cases, you have to be careful. So if you want to refer to the one particular component, you should say that summation convention is not being used. Okay. Otherwise, if you don't, then it will be taken to be the trace of that matrix. All right. So as an example of this, let's say I take the trace of a matrix, and using the summation convention, I can write this trace as AII, CII. Now, do you remember that C is this product of two matrices, right? AIK, BKJ. So I can write this as AIK, BKI. No need for any summation signs, because otherwise, if you didn't use the you would need two sums, right? A sum over I and sum over K. But here we are doing away with these sums. These sums are not needed. This is the summation convention. Okay. Then similarly, let's say you have two vectors. Well, okay. And so you have a matrix multiplying a vector, right? So how do you write this? You say that you have some vector u and some matrix A. This gives you A acting on u gives you V, right? So you have some matrix A and you have some vector u. You multiply these, get some vector V. Once again, we can use the index notation in this following way. We can write V of I is equal to A of ij uj, right? So summation convention. Einstein summation. Okay, well, that becomes too complicated. I'll just leave it like that. Okay. Just write summation. Okay. So we will be using this index notation throughout our course. And when we talk about four-dimensional vectors, four-dimensional vectors or tensors, and remember, tensors are just a kind of a matrix, okay? But I will explain what a tensor is. Okay, don't worry, don't be afraid of the word tensor. We will use indices mu nu, which go from we will use lowercase Greek indices like mu nu, alpha, and beta, which take values in 0, 1, 2, 3. All right. So, so for instance, if I have this this space-time point, how would I write down the components of this space-time or this vector, this 4 vector? I would write it like this. I would say x mu, right? And this means is defined to be the vector t x y z, or better not t x y z is the vector x0, x1, x2, 3. So these are the spatial components, and this is the time-like component. Okay. So when I want to talk about when I want to take the dot product of 2 4 vectors, how will I do that? I will write something like this: x mu, y mu. Now here I have done one new thing. I have raised and lowered indices. This raising and lowering we will talk about next time. Okay. But what is this dot product? This dot product will be x naught, y naught, x1, y1, x2, y2, x3, y3. So now here you notice that there is a minus sign in front of this component. All of the others, there is a plus sign, but here there's a minus sign. So I can also write this in the following way. I can write it as minus x naught, y naught plus x dot y. What is the vector x? Vector x means I'm referring to the spatial component of x. Vector y means I'm referring to the spatial part of y. Right? So this is just my usual spatial dot product. But then for the time-like part, I have a negative sign. So this is the fact. This negative sign is what tells us that these vectors x mu and y mu, they live in the space R31, as I told you earlier, R31 rather than R4. So this 1 denotes the fact that when you write down a metric on these 4-dimensional vectors, the time-like component has a negative sign. So in the next class, we'll talk more about where this comes from. But in the meantime, I'll just leave you with this definition of the Minkowski metric. It's just a diagonal metric with -1, +1, +1, and +1. So if you take this x mu, y mu, and whether you raise or lower its indices, it doesn't matter. You get the same answer. And you can write this as n mu nu x mu y. Okay. So, or again, eta mu nu x mu y mu. And here again, we have the summation convention. So if you put in the expression for x mu, what is x mu? X mu is this. And similarly, x mu would be like this, with the index lowered. And so if you put in this expression for x and for y, and you multiply by this matrix, you will get precisely this expression. Okay. So I'll stop over here because now I have to start my next class, which is scheduled to begin in two minutes. So if you have questions, please save them or ask them on the WhatsApp group or Telegram group, or you can ask them individually. All right. Otherwise, I will try to answer them in the next class, which will be tomorrow morning at 9 a.m. Okay. I will see you then.